Hi, welcome to this lecture. In this lecture, we will be talking about quantum feature spaces and quantum kernel methods. In the previous lecture by Bryce, you will have learned that a lot of the commonly used classifiers that are referred to as quantum neural networks or variational classifiers essentially boil down to being just a linear classifier in some sense in a kernel space or in a feature space. And so what we'll do in this session right now is basically we'll try to explore that in a bit more detail, give some more of the formal background, lay out the structure a bit about that space, talk a bit about what relevant feature mappings are. We'll talk about an algorithm of how to actually estimate kernel entries and what it is that you actually would do on the quantum computer and how that feeds into other algorithms. And lastly, the very important point we'll talk about is what kind of maps ultimately we would like to have and what maps we would not like to have as being the feature maps. And in the next session, Jen will tell you about choosing good maps and ways of doing that in practice. And this is more of a theoretical background lesson leading up to the next lesson. So before we dive into the quantum feature spaces and kernels, let's just go briefly over the basics and review some classical feature space tricks and the kernel trick before we dive in, so you know basically where everything else is situated. Okay, and so what is the basic idea of using feature mappings and kernel methods? The basic idea is essentially that you would like to use linear statistical methods such as linear classifiers, linear threshold functions, and apply that to problems that are not linear in nature. So the feature map is the following, and it's a map. Let me write that down. The feature map is a map that takes from a datum from some data space, right? And maps it to some feature space. So a feature space is typically a Euclidean space, which is fitted with an inner product. And so the map that you're looking for, let's call it the feature map, takes you from the data space into the feature space, and it takes an individual datum to point in that feature space, which is a larger vector space. Typically, those spaces are higher dimensional. And what we would ask is basically that that the space is essentially nonlinear, right? So what I would ask is that this map is nonlinear, right? And by that we mean, so this shouldn't be possible. So if f lambda x plus mu y is not the same as this, right, in general. You can have linear ones, but that doesn't really make a lot of sense, and you don't actually get to profit from them, right? So let's look at an example first before what we mean by that kind of map. So typically, the idea is it takes your data space, maps into a higher dimensional space, and what you would like to do is like have that encode the meaningful features of your learning problem. We'll talk about what that means a bit. So suppose someone gives you a learning problem where you have to basically classify X's and O's. And what you would like to do is use a linear classification method in the sense, right? What you will see, the way I've drawn this right now in this cartoon, you won't be able to put a linear curve through this. You will, but some polynomial curve like this would do and separate that. So what you can do is basically, let's look at this example. The data space in this case would be some subset of your rectangle, right? And you would take an x, which is an omega, and you can write it as two-component tuple. And then what your feature map could do, for instance, let's call it this one, is it would take this tuple and map it to a longer vector that looks like this. 2x1 times x2 squared. Right? Now this is a vector that sits in a 6-dimensional real space. If it started out with the in a 2-dimensional real space, and now we'll talk about what the individual components here of that vector, like this one here, those are the features. So in principle, what you want is, if you think in more general terms, is that these features basically go and compute valuable information of your data, right? So distinguishing attributes of your data, which you then later use to classify. That's sort of the idea here. And in general, it's a map that, as we said before, is supposed to go in a high-dimensional space, or it could potentially go in a much higher dimensional space, so even an infinite dimensional space. And then the hope is that that space, the other picture that you could take, is in that space your data becomes linearly separable. And if you take it back down to the original space, it looks like your decision surface is now becoming a curved surface if you map it back down to the lower dimensional space. Okay, so the fact that this is a high dimensional space makes it often awkward to work with this. So as Bryce has introduced support vector machines earlier, and what you will realize is in those support vector machines, you will have to solve an optimization problem, and you would need to solve it in that high dimensional space. But it turns out that in many practical applications and most of the relevant applications, you don't really need to know the entire explicit feature vectors. You only need to have some sense of where it lies within the feature space relative to other feature vectors that you're trying to classify, right? So we have to introduce some form of a distance metric, and that's roughly where the kernel function enters. So the kernel function that we'll talk about in a bit is a function that lives is in conjunction with depends on the feature map and lives in the feature space, and it is a function that basically takes 2 arguments, both from the data set, and produces a real number in the end. And so what it does is basically it takes 2 data points, maps it to x, y, the kernel function, which happens to be the inner product in that Euclidean space between the two feature vectors. And there's a neat interpretation of what this is, or what this is good for. I mean, it's simply Euclidean product in feature space, but what it does is it serves sort of as a distance metric when you want to classify a thing. So suppose, let's draw a little cartoon here. Suppose you have 2 feature map points, phi x and phi y, and you want to know how far apart they are, and you measure that in sort of your conventional 2-norm distance, then what happens is basically you can express this entirely in terms of the kernel function. How do you do this? Well, if you write down their distance, this is the same as this function if you write it out by expanding into the inner product of the standard Euclidean inner product. So what the kernel function in some sense does, gives rise to it's just an inner product function, but it allows you to basically measure distances in feature space. And the entire trick here is basically that it may be easier to just know what that kernel function is, as opposed to actually having to go and computing the feature vectors explicitly themselves, right? So to go into an example, let's look at this. If we take our feature vector earlier on that we had, that we produced above, so it's that the polynomial feature kernel that we have here, right? And we want to write down what the inner product between those two is, between two different data points, which we say is now the kernel function. If you do the math and you work that out and plug that in, which is I would encourage you to do, you will realize that this is simply just this kernel function, meaning you compute originally the inner product between those two data points in the low dimensional, in this case, two-dimensional space, add one, and then square it. And that is about the same, that's the same inner product in this very high dimensional space that we looked at. In this case, it's much easier to evaluate this. There's now many other examples that you can choose. And the trick is in many cases that what people do is they don't ever go use the feature space explicitly and directly, but what they do is they go and just define kernel functions and it's in such a way that they're inner products. There's a condition to this. We can say there's the converse is essentially possible. You say you start with the kernel function, and that defines in the end what your feature map should be and the what the feature space, the Euclidean feature space is in the end. And the condition that you have to satisfy is something called Mercer's condition, which I will not write out, but essentially requires that kxy gives rise to a Gram matrix, so an inner product matrix. It just asks that kxy is a positive semi-definite form. So and that means you can actually, there are some very standard examples that people use classically. So for instance, just general polynomial kernels that we had one example of before. And they look like this. So you have your standard smaller dimensional inner product, but then you add +1 and raise it to the dth power, which is a legitimate inner product. Or another one that is commonly used are so-called radial basis functions. And they're just distance like this. And both of them give rise to positive definite forms. Both of them satisfy Mercer's condition. So you don't ever actually have to go into that feature space. And in the case of the radial basis function, that feature space is even infinite dimensional. It just suffices to work mostly only with that kernel function, right? And so what we try to do here right now is to insert a point where these kernel functions come from a process on a quantum computer, right? So our goal is to come up with kernel functions that are sort of interesting from a quantum mechanical sense, and you don't have access to them classically without a quantum computer, and use them to see whether we can classify certain data better than we could have otherwise classified them, because we could extract features better from that data using a quantum computer than we could have extracted it by using these classical kernels. Okay, that's the entire the game that we're playing here. Okay, and to that, let me basically walk you and run you through the picture of quantum feature spaces and what we think a good way is to think about them. And let me drive in there just now. So with that, we follow the definition from this paper. You want to look it up. And if you want to look it on the archive, you can find it there as well. Under that identifier 736. Okay, so before we dive into how we define those feature spaces, let's do some really basic linear algebra and just do a small recap. And we're going to look at the vector space of matrices. Right? Little trick, depending on where you stand, you probably know this already. But so if someone gives you two n by n matrices, so let's sit in this space, these matrices in principle, they form a vector space. So in which sense? Well, if you take two of those and then take a bunch of scalars, then you can essentially add them. And they end up being, again, n by n matrices, if you define the addition correctly. So you do component-wise addition multiplication. So if you write this out in an example of 2 by 2 matrices, then what you look at is alpha A11, alpha A21, alpha A12, alpha A22, plus beta B11, and so forth, beta B22, and you just ask that you just add them component-wise. Okay, and that's of course a vector space. And the nice thing is that vector space also comes with an inner product between two matrices. And that's sort of the so-called Hilbert-Schmidt inner product, or the trace inner product. Okay, and how is that inner product defined? Well, what you do is you basically take for two matrices, say A and B, you write it out like trace A dagger, take the Hermitian conjugate, B, which is the same essentially as explicitly writing out this sum. So you take the matrix element Aij, take the complex conjugate matrix element Bij, multiply them together and sum over all the indices. Okay, where if you haven't seen this yet, the trace function is just the sum of the diagonal, some matrix. So you can try this out. So you multiply these matrices, one conjugate with the other, sum over the diagonals. This is the inner product you end with. So you can check yourself that this actually forms an inner product, satisfies all the conditions. And now what we have is we have a vector space of matrices where essentially addition, multiplication with scalars is possible, and an inner product is given. So it's a standard Euclid. It's a Hilbert space effectively that you're working with. Okay, and so you could ask, so what is the dimension of that space? And the dimension of that space you can count as like, you can wonder like how many different linear combinations are there? And what you'll realize is if you look at them, you can look at every entry of the matrix by itself, and that's sort of a basis by itself. You realize if it's an n by n matrix, there's n squared many linear independent matrices under the condition. So it's an n squared dimensional vector space. Okay, so why do we go through this? The reason is this will essentially be the Euclidean space in the end in which we define and which we promote to be the quantum feature space. Okay, and to do that, we're not going to run through the general theory. We're just going to look at a single qubit example for now, for starters, right? So let's look at a single qubit example. So if you recall from the session this morning, Bryce will have told you that all these quantum neural network classifiers or variational classifiers reduce to linear threshold functions. And if one were to sum that up, basically, what all these classifiers effectively do is the following. So those classifier functions, say call them f of x, and depends on some variational circuit w, compute this function. Okay. Right. So where now w hat is going to be a +1, -1 eigenvalue observable. So you can imagine this, okay, there's some variational circuit, W theta, there's a diagonal matrix with +1s and -1s on the diagonals, and there's conjugate, so it's still an observable, conjugated by some circuit, and so you can look at a specific example for a single qubit. This is just this matrix, and say a Z matrix in the middle, right? And whereas this phi x is essentially a vector that you prepared by loading your data by some unitary circuit ux0. Okay, so you've been through that in the previous session. Now, a convenient way of writing this is you can use the Hilbert-Schmidt inner product into matrices, and then you immediately see what's going on, is because you could write this classifier simply as the sign of trace by x times w hat, which is just rewriting what I wrote earlier, or if you recall the definition of what the inner product is, it's just phi x w hat, Hilbert-Schmidt inner product, where we have just now written this rank 1 density matrix or projector that you came from as capital phi of x. Okay, and now there's an interpretation so that this allows us is, okay, this is actually a linear threshold function. W hat is an observable, but it also functions sort of as the normal of your hyperplane that separates this. And this is a density matrix of rank 1, but it serves as our feature vector. Okay, so that's the picture. So what we have is now basically looking at this, you immediately see that, okay, what you actually have to define as your feature vector are these rank 1 projectors in that matrix space. And the normal, which is an observable, is going to be just a matrix in that space as well. It's going to cut everything in apart. Okay, so for a single qubit, we can choose a very nice basis that you may already be familiar with, and that's the single qubit Pauli basis. So what are the Pauli matrices? So these are essentially the identity matrix for a single qubit, the X matrix, the Y matrix you've seen before, and a Z matrix. And they have the nice property that they form an orthogonal basis set with the right Hilbert-Schmidt inner product. Meaning, so what you can check is, for instance, if you take the inner product with two of those matrices by themselves, for example, if you take trace x dagger x, which is sort of the Hilbert-Schmidt inner product between xx, then x dagger x is essentially the same as the identity. It squares to the identity, as you can check. So this is 2, right? However, if you now do the same thing with x and z, you will realize that this is the trace of the following matrix. And you see the diagonals as 0, so this thing is traceless, and it's 0. And so what you can check is basically all of these matrices under the Hilbert-Schmidt inner product have exactly this property that if you square them themselves, they give the identity. If you take the inner product with another one, they give you 0. And so what you can do now is you can expand our example state into that basis. right? So the first one is, okay, with the identity, it's just the trace of this thing by itself, plus this guy, plus all the way to the last guy. Right, and you just rewrite this, you'll realize that this is something you've learned earlier in this course as well. That's the Bloch representation, or the representation of a density matrix on the Bloch sphere. Likewise, you can also expand your observable this way. And so the interesting thing here is, by the way, this is trace 1 because it's a density matrix, and the way we set up the observable is that the trace of the observable is always 0 because it's just essentially rotated Z matrix. And if you now expand the observable in that Pauli basis, you're going to end up some coefficient omega x, some coefficient omega y matrix, some coefficient omega z matrix, where omega x is just essentially trace x w hat, and the other ones follow the same way. Okay, so why have we done that? It's a nice case because you realize everything that's going on is only happening effectively in 3-dimensional space and in a Bloch sphere, so you can nicely visualize what's going on. Let me include a brief a graphic here. And explain this graphic. So this is our scenario that we're having. So our data space that we've been looking at is this space omega here, and omega is essentially just the interval from 0 to 2 pi. This is one example for a qubit, and we say the red parts are sort of plus labeled, the blue parts are minus labeled. Again, red parts are plus labeled. And there's now going to be a feature map, and that feature map is going to be described by some unitary circuit UX that we've talked about, and that's going to take you into the Bloch sphere. So, this is what's going on. So, to explain that, what is that unitary map X that you can see here in that picture? That unitary is basically the following sequence. So first apply a Hadamard gate on a single qubit, where you know a Hadamard gate is 1, 1, 1, minus 1, 1 over square root of 2. Then you apply a Z phase gate by X, so you're applying e to the I x half Z. Then you apply another Hadamard gate, right? And then you apply the same ZX gate again. And this entire thing basically corresponds to a single qubit X rotation. So what it does is basically it takes, it prepares the following state. It prepares the state phi x, ux, u dagger x. And what you can see here is now what this traces out this 8 shape on the Bloch sphere. And we chose some random W here, which cuts this Bloch sphere into 2 parts and has a normal vector here. And what you can see is that everything sort of north or to the left side of that normal vector is colored in red, corresponding to the plus label. And everything on the opposite side, the downside of that hyperplane, corresponds to minus, corresponding to the minus label effectively. And so the curve that you're seeing here essentially corresponds to just computing the value of this inner product and then assigning the labels depending on whether these curves are on the plus side or on the minus side or positive. Okay, so this is an example of how that feature mapping works. for a single qubit. The component basically of which feature map you chose is determined by this unitary u of x. And that basically traces out some nonlinear surface in the in quantum state space. You can, right? So why do we have to go to this matrix space, and why do we worry about that? And maybe there's you could ask yourself the question, so what about just using your standard quantum mechanical Hilbert space? Just take these guys, and why you run through all these exercises of doing that as a matrix space. And that has actually been proposed in the following paper. And depending on how you interpret this, then you can run into some problems if you do this, right? And so if you take, for instance, this to be the feature vector, then the normal has to be another vector in that space, meaning your normal is also going to be like a quantum state, and both of those things essentially live in this vector space. Okay. So, and if you do that, you could wonder, okay, so if I want to stick to my standard formalism, I would like to have a binary classifier and assign the following sign rule to this inner product. Then the first thing is you're going to observe is, okay, well, in principle, this thing doesn't necessarily need to be real for starters. So it could be some complex number, but suppose for now you chose things right, and it is. There's a problem in there in the following sense. If you define the feature space this way and define the classifier that way, you have to be careful, because what can happen is essentially what happens is these vectors in quantum mechanics are only defined up to global phase, meaning I could write down phi of x, and that is physically equivalent to writing e to the eta phi of x for some global phase, where eta is some real number, right? And physically, there's no difference between the two of them. So if you call this guy phi twiddle x, everything that you try to observe, say all these expectation values that you might compute, they're just the same, independent of the global phase that you have here, right? So, but your classifier happens to become sensitive to the global phase if you do it that way. So why? Well, imagine you basically say you chose everything right, and this is now a positive number. Then physically, this is the same. So they're sort of equivalent, but this is a negative number. So which label do you assign, right? So what happens if you define it this way, you run into the problem that things are only defined up to global phase, and that might make sense to write it down on pen and paper or do numerics with it that way. But in a physical sense, there's not really much of a distinction between the plus and the minus sign, so it's very difficult to assign the labels correctly, right? And what you could do is essentially, I mean, there's ways you could try to fix this. One way you could try to fix this is basically and go and just define that always the relative phase, but then the relative phase that you're trying to define actually contains the information that you want to learn from the classifier in the first place. Likewise, if you define the kernel matrix this way, and you use that standard bracket inner product, then you have to be sort of careful that you assign the signs consistently across all those things, which is something that's actually physically not that doable. All right, so That's why we prefer to work in that matrix space effectively. Okay, so now let me basically summarize the general n-qubit feature space, right? So the feature mappings that we consider are the followings. So let's take some data from your data space and assign it to some quantum state. So rank 1 projector. By applying some unitary circuit U of X. We'll talk a bit about that unitary circuit U of X. You could now wonder, so what is the resulting kernel matrix that you get from that? So what you have to use is you have to use the Hilbert-Schmidt inner product now between those two density matrices, the trace inner product, however you like to call it. And it turns out, if you work that out, that this is simply to the fidelity between those two vectors. Now, this is a measurable and tractable quantity. You'll realize it's real and it does not depend on the phases. And it's actually also always positive. So it's always a kernel with positive entries that we're considering here, right? And if you want to write this out in terms of the matrix U of X that prepares the data and the feature vector, looks like this. We'll talk a bit about that because this is going to give you a way of actually measuring this. Okay. So then the next question you may ask is, what are actually the features here now? And so what you can do is you can choose a matrix basis that is sort of Hermitian, exists. And then you realize that the features, so the individual components of your feature vector, by the inner product of this and the feature state, they're just the expectation value with respect to those different observables. Okay, and if you want to write down what the resulting linear classifier is in the end, then we had that before. It's essentially just the sine function and if you write it out in that basis, it takes the familiar form. Right, so. Okay, we're here now, the W alphas are just components. You're separating normal with respect to that particular basis. Okay. So the crucial point is, how do you get your data in there? As we've as Bryce has explained before, that happens through the feature map circuit U of X, which is some form of the unitary circuit. And in a bit, we'll talk about how to choose those. Okay, so we'll move on now to the point and ask, right, now we've defined all those things. There's very little direct things that tell you what it is that you actually want to compute or have to compute. And we'll get to this point exactly now. And so we'll talk about quantum kernel estimation. just now. Okay, quantum kernel estimation is the following observation. So what you know from classical feature space and kernel theory is that you don't actually want to work directly with the feature vectors. What you want to work with in all of your algorithms is just the kernel function, right? And so what you need is a way of basically getting that kernel function from the quantum computer, and that way you can essentially use that kernel function in many classical algorithms that we will talk about. Okay, and so if we now go basically and look at how the kernel is actually defined as we did before, what we do is we use the quantum computer to estimate the following kernel function. Right, so it's the fidelity between those two states. And we can write it out like this. So this form already here actually gives you a hint of how you can actually measure and estimate this. Because what you can see is that this is essentially just a transition amplitude. Right? So this is a unitary that's somewhere here in the middle. You start in the 0 state and you want to ask, what is the probability that you end up back in the 0 state after having applied uy in u dagger x? Right? So if you want to draw this as a circuit, what you do is essentially start out in the 0 state and prepare everything. And then what you do is you evolve forward with your feature map unitary uy. Then you go and evolve backwards with the same unitary but a different datum x. And then you go and just measure in the z basis. And count how many times you see 0. Okay, so what you can see is basically you start 0, you evolve forward in uy, then you evolve backward with u dagger x, and you count how many times you see 0. And that transition amplitude, the probability of you seeing the 0-bit string on the outcome, is actually exactly your kernel value. And there are other ways of doing this. You can prepare swap tests and so forth, but this is sort of the one of the most economical ways that that we're aware of. So formally, what you do is you set some counter r equals to 0, and what you're going to repeat now r times is the following. First, you prep the 0 initial state, then you apply the unitary circuit for uy, then you apply the inverse of that unitary circuit for datum x, and then you measure in the z basis, and if you see the all 0-bit string, you set the counter, you increase the counter by 1, and then you repeat. And after you've done that r times, you declare the following estimate, the kernel between x and y, to be just r divided by capital R. And what you see is basically now you basically go and sample the kernel time by time by time again. And effectively what you're producing with high probability, you're producing k hat is an estimate of your kernel matrix up to some additive sampling error R. Okay, so good. So this error is actually kind of important because you'll realize that the hardness in which you measure, like how difficult it is to do your kernel and to compute that, has to compare with the fact that your quantum computer can only produce additive error sampling errors, and we'll talk about this in a bit. Okay. Now let's talk about why this might be interesting as a near-term application. So what do we mean by that? What we mean by that is sort of, as you probably heard throughout the course beforehand, in the spirit of this this entire school, is you want to know what it is that you could do with the quantum devices that are going to be available soon or are available now and already. And these are devices that are sort of in the order of 50, 60, up to 100 qubits, potentially larger in the coming years, but they will not be error corrected, right? And so they will be noisy devices, and you sort of have to restrict what it is that you want to compute on them and hope that even in spite of the noise, you might be able to still compute things that you don't have access to classically, right? And so if you look at the circuits that we'd like to run here, the only part you do on a quantum computer, talk about that in a second, are these just estimating these transition amplitudes up to an additive error, right? That we've talked about earlier. And the one nice thing is that what you realize is that this k hat is actually an expectation value. And if you are in the fortunate situation that your circuit is not too deep or is a relatively shallow circuit, where shallowness is basically measured in terms of how coherent and how long your device can accurately compute, then there are tricks to basically produce relatively accurate expectation values. While the statistics are still wrong and many other things are still wrong, you can still produce relatively accurate expectation values by a procedure called error mitigation. And this is why this might potentially be an interesting thing to try out, because the only reason, the only component for which you need to use a quantum computer is exactly just estimating these transition amplitudes. And a lot of the more complicated processing tasks actually can happen within the context of a classical algorithm that only relies on getting access to that kernel, right? And so let's talk about some of these algorithms for which you would like to use this quantum kernel estimation routine, right? And so there's a long list of algorithms that you can consider. And in principle, what you could do is basically, if you want to look for other places where you could use this, what you could do is essentially you could, wherever you find that classical kernel methods turn out to be useful. So options are, for instance, or you could have them in regression, in ridge regression, logarithmic regression, in function approximation, and clustering. And all these places you can, in principle, ask yourself, so what happens if I insert a quantum kernel at that point, and instead of using a classical kernel, and this way see whether there's something interesting that you can do that you couldn't have done classically beforehand. That is challenging to do, right? But what we're going to look here is the most simple example, and that's essentially we're just going to look at classification. And Bryce has introduced the support vector machines earlier, and so we're going to see now exactly where the quantum kernel enters here, right? So in the classification problem, suppose you're given a set of labeled training points, right, where all the xi's, they're the data space, and the yi's are just plus and 1, -1 labels, and these are the training samples. And what you would like to do is now train a classifier to correctly predict these training samples, right? And so what you do in the context of an SVM that uses the dual description, which uses the kernel, you actually do the following training procedure. You solve the following optimization problem. You maximize overall alphas. Subject to these constraints. So what you have here is you have a quadratic program, and that quadratic program depends on the kernel matrix here. And you try to optimize these Lagrange dual parameters that were introduced earlier in the previous lecture. And but you do this now with a kernel where you actually went and estimated for all data pairs this kernel matrix on a quantum computer. The algorithm itself is a purely classical algorithm. It's the standard SVM training algorithm that you use. The only difference is now that you actually, this time, you used a quantum computer to call the kernel matrix and estimate that one on the quantum computer. So for training, what you have to do is essentially, if you do this for all the training sizes, you have to perform m² many times the kernel estimation routine to get the k-hats, and then you can feed that into the classical algorithm, and as an output, what you will get is essentially the optimal parameter alpha i's, right? And so if you're now ready to use your classifier, you just need to use those optimal training parameters that you just computed. And suppose now a new datum comes along for which you do not know the correct label, then you could use that classifier in the following sense. You say, well, you want to assign the label according to this rule. Right? And so in order to do this and to classify the data again, what you will need to do is you will need to use the quantum kernel estimation routine on the quantum computer again. So which means then whenever you want to predict the correct label, what you have to do is you have to compute the kernel matrix between all the training points that contribute to your classifier and the new datum, and then sum that up and compute the signed function. Okay, so that is one example where essentially you used an entirely classical algorithm, and the only part that uses a quantum computer here is to just estimate those inner products, right? And what you need for that is just the estimation of the transition amplitude. So in the same sense, you can try to look where you can also apply these kernel estimation routines in other settings. Right, and now this is the rough framework. Now let us talk about your choice of the unitary feature map circuit U of X. So there's, in principle, multiple things you could do there. So what you want, of course, is that U of X is a unitary circuit. Depends non-linearly on the datum X. And but importantly, so those X are essentially gate parameters, as we've been seen before. What you want is that using this, you could now go and actually think of classifiers or think of learning problems that you wouldn't have had access to by just purely classical means, right? So then that means you have to set a couple of conditions on that kernel entry in the transition matrix, right? So what you would like is you would like to be able to use that to compute features that you don't have access to classically. We'll talk a bit about what not having access to classically means in that context. It means, for instance, as at the very least, it should be difficult for a classical computer to estimate this quantity. Right? And here one has to be sort of mindful, because we on a quantum computer, we only estimate these things up to an additive error, right? If you recall correctly. And in your choice of the kernel, you have to wonder, well, how well could I do this up to an additive error with a classical computer as well? And so let me first, before we dive into some thoughts on what you actually have to do, let's look at a couple of trivial examples. Okay, and what do we mean by trivial examples here? They're all classically tractable, right? We say they're classically tractable is at no point do you actually need to use a quantum computer to evaluate those. So you don't expect that you gain a lot from over classical classifiers by using these examples. Okay, so let's look at the first example, which is product states. Right, so what you could do as your feature map circuit is you could say, well, I have, say, I'm going to take my data, which is an X vector, which has, like, say, xn components, and I'm going to put a bunch of single qubit gates here. That each individually depend on individual datum, right? So this is now going to be my full circuit U of x. It's just going to be the tensor product of individual single qubit rotations. So one example for that could be, for instance, I'm just going to make them to be XY rotations. Right? And so why is this immediately classically tractable? Well, if you compute that between x and z, you look at the transition amplitude, and what you see is they factor out. Because it's a tensor product, they individually factor out. And what you can do then is basically, you can go and compute each of them individually. Right? So what you can do is, for instance, in that example where we chose this matrix, what happens is that for, say, one of these guys by themselves, that happens to be just the cosine between those two squared. So you actually have a complete analytic description of that kind of kernel. And so this way you don't expect that that type of feature map does better than a classical feature map, very much because this effectively is a classical feature map that you can compute directly. Just takes you linear number of computational steps in order to compute that feature map. There are a couple of more examples like this, and I'm just going to name them. They're referred to as amplitude encoding. Where basically you take your vector x1, xn, and essentially write them as just that vector, and then compute the inner products for this one. Another one is, if you're familiar with bosons, so it doesn't apply to qubits, essentially are so-called displacement operators, which give, or essentially coherent states, and they give rise to Gaussian RBFs. And the amplitude encoding ones, they give rise to polynomial kernels, which are all classical kernels. So they by themselves, actually, they don't necessarily classify bad, because in the classical literature, they've been used a lot, and they do a very good job in principle. But it's not something you would need a quantum computer for, because you can do it immediately classically. Let me go into another subtle example. And those are referred to as IQP circuits. So you realize, okay, if product states don't work, then how about we add some entangling gates? Okay. And so what you can do there is basically is the following setting. Say, let's look at this type of circuit where you apply, first row of Hadamard gates. And then you apply a phase gate here as your feature map circuit phi of x. Now this is your circuit U of x that you might want to consider. Okay, where now this phase gate phi of x essentially just e to the I. You could make it this if you like. There are other choices as well. essentially v phi of x is just a diagonal matrix with a bunch of phases on the diagonal. Okay, so that's effectively what it is. So so this is now a circuit that has entanglement in it. It's not a product state that factors out. But if you look at the kernel that corresponds to that circuit, it sort of looks like this, right? And so it's essentially another phase circuit in the middle. So you have a bunch of Hadamards, a phase circuit in the middle, another bunch of Hadamards because they add up. And you can actually express that kernel simply as the sum. So you sum over all small z's that are plus minus 1, the n. I right, phi is squared. And what you realize is, okay, fine, you know, people know that this quantity itself is actually that looks horrible. Let me erase this again, I'll write it out clear. So this kernel looks like this. Looks like this. So the kernel is cake xy, and it's essentially a uniform sum over all plus and minus 1 bit strings So all of these are phases you have here, and it's an exponentially large sum, of course. And to evaluate that sum exactly is actually very, very difficult. It's sharply hard. People have shown that. But to estimate that sum up to an additive error is actually pretty easy. All that you have to do is draw the zi's uniformly at random, and add up all those phases, and that's a bounded variance estimator. So you can easily get an estimate for this kernel up to an error epsilon with 1 over epsilon squared many samples, which is just the same as you can do for a quantum computer. So there's not much of an advantage here because of the additive error problem that we talked about beforehand. Okay, so then the question is, what does actually work? And the answer is there's very few examples. There's only one formal example, which I'll basically just give you a pointer towards in the end, where there's a provable separation between what you can learn classically and what you can learn quantum mechanically using that method. But as a general guiding principle, you could wonder about what are actually some good kernels that you could come up with yourself. And so let me give you some suggestions where you could start looking, essentially. And Jen is going to give you in the next lecture a very comprehensive overview, and it's going to show you in a bit more detail. So what you can do is essentially take what you know and modify it in some way. So for instance, the product case, which we know is trivial, is basically just a bunch of gates that you follow this way, right? But what you could do is you could basically take the root of those gates, you can split them up, or you can do other combinations and actually just map it. So this is the data x1, x2, x3. You could go and intersperse that with a bunch of entangling gates, right? And then continue. That's one suggestion. The other thing is, this is something that we've done in the paper that this work is referring to is, for instance, we've gone and taken this IQP circuit that I had discussed beforehand, with that phase gate. We just essentially doubled it. Right? There's a reason of why that becomes interesting then. It's because that kind of circuit has an oracle separation. It's referred to as threefold correlation. It was introduced by Aronson and Binus. And then it starts to become interesting. So you see, there's many options where you can essentially play around with and modify the circuit. So the important thing, though, is you have to be mindful that your circuit is not too complicated either. Because what can happen is basically that if you take a very generic, a very random circuit, you will never see the zero output unless you actually use the same data, which means your kernel matrix in this extreme case is just going to reduce to roughly the identity matrix with almost zero in the off diagonal. And that doesn't contain a lot of information. So you have to, it's really an art and a balance to find what the right ones are. And Jen will talk to you about that in the next lecture and next session. And I will only mention that as of now, we only know for one example, which is called, which we refer to as the D-log example. And let me give you a reference for that, if you care to look. And that's the only example that we are aware of currently for which you can actually formally prove start to finish that learning classical data with that with the quantum kernel method is actually advantageous over classical methods, meaning we cook up a data set, an example, where you can actually argue that relative to the assumption that there's a very difficult task that classical computers cannot solve, which is solving the discrete logarithm problem, that no classical classifier actually was able to classify that data, while these kernel methods we show actually do classify the data arbitrarily well. I will not go into those details, but one thing one can take away from that is that, yes, there's a separating example. However, that example is very artificial and very constructed, so it may not be applying to a real-world problem that you might care about. Which means then going forward in the next lecture, Jen will teach you about good choices for coming up with quantum kernels and good ways of basically tweaking quantum kernels to match your data and get classification results. So with that, I would like to thank you and thank you for your attention, and hope you have a nice remaining summer school. Thanks.